At the start of World War II, armies prepared for tanks, aircraft, and artillery, but few fully understood that fuel, not firepower, would decide how far an army could move. In the early years of the war, thousands of vehicles across Europe were not destroyed by enemy fire, but abandoned simply because they ran out of gasoline. Fuel transport was slow, messy, and unreliable. Most armies still relied on fragile drums, open cans, or improvised containers that leaked, rusted, or collapsed under pressure. Germany approached the problem differently. As Blitzkrieg demanded speed and constant movement, German engineers realized that a modern army needed a fuel container as reliable as a weapon. The result was the Jerry Can, a deceptively simple steel container designed to survive combat conditions. It could be dropped, stacked, frozen, or transported across deserts without leaking. Soldiers could carry it alone, pass it quickly along supply lines, or pour fuel without funnels or tools. The impact was immediate. German armored units advanced faster because fuel arrived when and where it was needed. Meanwhile, Allied forces struggled with leaking cans and wasted fuel, especially in North Africa. British and American reports later admitted that fuel losses were staggering, sometimes more than 40%, simply due to poor containers. By the time the Allies recognized the Jerry Can's importance, it was already shaping the war's logistics. It proved that victory was not only built on tanks and planes, but on small, intelligent designs that kept an army moving. In World War II, the Jerry Can became a silent weapon, one that carried the war forward, mile by mile. At the outbreak of World War II, military planners obsessed over tanks, aircraft, and firepower, yet one overlooked weakness threatened every modern army: fuel delivery. Mechanized warfare depended on gasoline, but most armies entered the war using outdated fuel containers, thin drums, fragile cans, or open-topped vessels that leaked, rusted, and failed under stress. Vehicles were often abandoned not because they were destroyed, but because fuel never reached them in time. Germany confronted this problem early. Blitzkrieg demanded uninterrupted movement across vast distances, often far ahead of rail lines or fixed depots. German engineers understood that speed would collapse without reliable logistics. In 1937, they developed a new steel fuel container built for war, not warehouses. It was compact, airtight, and strong enough to survive being dropped from trucks or stacked in columns. This was the Jerry Can. Unlike previous designs, the Jerry Can could be carried by one soldier, shared by two, or rapidly passed hand-to-hand thanks to its three-handle layout. Its sealed cap prevented evaporation and spillage, while the reinforced body resisted denting that would trap fuel inside. Soldiers could refuel vehicles quickly without tools, funnels, or wasted time, an advantage that mattered under fire. The effect was immediate on the battlefield. German armored units advanced farther and faster because fuel arrived consistently. In contrast, Allied forces in the early war years suffered enormous losses from leaking containers, especially in the North African desert, where heat, sand, and vibration destroyed inferior designs. British reports later admitted that up to 40% of fuel was sometimes lost before ever reaching the front. Only after capturing German supplies did Allied forces recognize the Jerry Can's true value. It became clear that this humble container was not just equipment, but a force multiplier. Before the first shots of World War II were fired, German military planners faced a problem that could not be solved with tactics alone. Germany's new doctrine of Blitzkrieg depended on speed, tanks advancing faster than the enemy could react, supported by motorized infantry and constant air cover. But speed created a dangerous vulnerability: fuel. Every kilometer gained pushed German units farther from supply depots, rail lines, and refineries. Germany did not possess limitless oil reserves. Much of its fuel had to be refined synthetically or transported over long distances, making every drop valuable. During early campaigns in Poland and France, German commanders quickly learned that tanks could outrun their own supply columns. Vehicles often arrived at objectives with empty tanks, waiting helplessly for fuel to catch up. Without a reliable way to move gasoline forward, even the most powerful armored divisions could stall. Existing fuel containers made the problem worse. Traditional drums were heavy, awkward, and required pumps or tools to use. Smaller cans leaked under vibration, spilled during transport, or collapsed when dented. Fuel losses mounted before supplies ever reached the front. In fast-moving operations, refueling delays of even minutes could mean the difference between encircling an enemy force or allowing it to escape. The challenge intensified as the front expanded. In North Africa, extreme heat caused evaporation and pressure buildup, while in Eastern Europe, mud and freezing temperatures punished weak equipment. German logistics officers reported that poor fuel handling slowed advances more than enemy resistance. Fuel was not just a supply, it was time itself. This reality forced Germany to rethink logistics from the ground up. The army needed a fuel container that could move as fast as the tanks it supplied, survive harsh conditions, and deliver fuel efficiently at the front. In 1937, as Germany quietly prepared for a future war, a small group of engineers was assigned an unusual task: design a fuel container that could survive combat. The requirement sounded simple, yet no existing container met the Army's needs. It had to be strong, airtight, easy to carry, and usable without tools, all while wasting as little fuel as possible. This was not a civilian product. It was a piece of military engineering. The solution emerged from careful observation of failure. Engineers studied how drums split under pressure, how thin cans dented and trapped fuel, and how open spouts spilled precious gasoline during refueling. Every weakness became a design problem to eliminate. The result was a welded steel container with an X-shaped reinforcement pressed into its sides, allowing it to expand and contract without collapsing. This single feature dramatically increased durability under heat, cold, and rough handling. Equally important was the three-handle design. It allowed one soldier to carry a full can, two soldiers to share the load over long distances, or entire lines of men to pass cans rapidly forward without stopping. The cap was sealed with a rubber gasket and opened with a simple lever mechanism, removing the need for tools and preventing evaporation or leaks. Early field tests were brutal. The containers were dropped from trucks, stacked high, frozen overnight, and exposed to desert heat. They were shaken on rough roads and submerged in water to test their seals. Unlike previous designs, they did not leak, rupture, or fail. Reports from testing units confirmed that fuel losses dropped sharply. By the end of 1937, the design was approved for mass production. What appeared to be an ordinary metal can was, in reality, the result of deliberate engineering choices driven by frontline realities. Before the war began, Germany had already solved a logistical problem that other armies would not fully understand until it was too late. At first glance, the three handles on the German jerry can seem excessive. Most fuel containers of the era had only one handle, if any at all. But this detail was not decorative, it was a calculated solution to multiple battlefield problems. German engineers understood that fuel delivery was not just about storage, it was about speed of movement under pressure. The central handle allowed a single soldier to carry a full can securely over short distances. The outer two handles, however, revealed the design's true genius. Two soldiers could carry the same can together, sharing the weight during long marches or when navigating rough terrain. This reduced fatigue and injury, allowing fuel to reach forward units faster and more reliably. More importantly, the three-handle layout enabled a human conveyor system. During refueling operations, soldiers could stand in lines and pass jerry cans hand-to-hand without stopping or turning their bodies. Each grip aligned naturally with the next, keeping fuel flowing toward vehicles even under fire. This simple mechanical advantage saved critical seconds that could determine whether tanks moved or stalled. Field reports from early campaigns confirmed the advantage. German units could refuel entire columns more quickly than their opponents, minimizing exposure time during vulnerable stops. In fast-moving operations, shorter refueling times meant sustained momentum. Blitzkrieg relied on never allowing the enemy to recover, and the three-handle design quietly supported that principle. The handles also improved stacking and transport. Their shape prevented cans from sliding during movement and allowed them to be hooked, tied, or secured easily. What appeared to be a minor feature became a logistical multiplier. In war, innovation often hides in plain sight. The jerry can's three handles were not about comfort, they were about efficiency, endurance, and speed. By solving several problems at once. Among all the visible features of the German jerry can, none was more misunderstood than the large X pressed into its sides. To many observers, it appeared decorative or symbolic, yet it was one of the container's most critical engineering elements. German designers knew that fuel containers failed not only from leaks, but from deformation caused by pressure, impact, and temperature change. When filled with gasoline and exposed to heat, internal pressure could build rapidly. In cold environments, fuel contraction created vacuum forces that crushed thin-walled containers inward. Ordinary cans dented easily, trapping fuel and making pouring nearly impossible. The X-shaped reinforcement solved all three problems at once. By stamping the steel into an intersecting X pattern, engineers dramatically increased the container's structural strength without adding weight. The folds allowed the metal to flex slightly, absorbing shock when dropped or struck, while preventing permanent collapse. Instead of buckling inward or bursting outward, the can maintained its shape under extreme conditions. Early tests proved the advantage. Jerry cans were dropped from moving trucks, stacked under heavy loads, and exposed to desert heat during trials in North Africa. Others were left overnight in freezing temperatures on the Eastern Front. In each case, the reinforced sides expanded and contracted safely, protecting both the container and its contents. Fuel remained usable, and the can could still be emptied completely. This design also improved efficiency. Because the can retained its shape, fuel flowed smoothly without airlocks or sudden surges. Soldiers did not need to punch holes, pry dents outward, or waste time correcting failures common with inferior containers. Every can delivered nearly 100% of its fuel. One of the most critical weaknesses of pre-war fuel containers was not their bodies, but their lids. Traditional cans relied on threaded caps that required tools, wore down quickly, or failed to seal properly. Under vibration, heat, and rough handling, these caps loosened. Fuel evaporated, leaked, or spilled during transport, wasting precious gasoline and creating constant fire hazards at the front. German engineers addressed this failure with ruthless simplicity. The jerry can's lid used a hinged, lever-locking mechanism combined with a rubber gasket that formed an airtight seal. Instead of twisting threads, the cap snapped shut under tension, evenly compressing the rubber ring. This prevented leaks, stopped vapor loss, and eliminated pressure buildup that could force fuel out during transport. The advantage in combat conditions was immediate. Soldiers could open the can with one hand, even while wearing gloves, without tools or funnels. In contrast, Allied cans often required wrenches or improvised tools, slowing refueling and frustrating crews under fire. With the German design, a tank or truck could be refueled in seconds, not minutes. Early field reports highlighted another benefit: safety. Sealed lids reduced fuel vapors, lowering the risk of explosions during transport or storage. In desert conditions, where heat increased evaporation, German units lost far less fuel than their opponents. In freezing climates, the rubber gasket maintained its seal when metal threads failed or jammed. Tests showed that the lid remained secure even when cans were dropped or inverted. Fuel stayed inside, and the container remained usable without repairs. This reliability changed how fuel was handled at the front. Soldiers trusted the can, which meant fewer workarounds, less wasted time, and less lost fuel. The rubber seal and quick-release cap were not minor conveniences. They were deliberate solutions to battlefield realities. When the United States entered World War II, it quickly discovered that its fuel containers were unfit for modern, fast-moving warfare. American forces relied on thin steel cans and large drums that leaked, dented easily, and required tools to open. In training and early deployments, fuel losses were severe. Vehicles often arrived at the front with less gasoline than expected, and refueling under combat conditions was slow and dangerous. The turning point came when Allied forces encountered German fuel cans in North Africa and Europe. British units had already captured and quietly adopted the German design, reporting dramatic reductions in fuel loss. American observers took notice. Field reports sent back to Washington described the Jerry can as superior in nearly every way, stronger, easier to carry, and far more reliable than U.S. equipment. With urgency rising, the U.S. military ordered an immediate evaluation. German cans were shipped back for study, disassembled, and measured in detail. Engineers were instructed to reproduce the design as quickly as possible. Speed, not perfection, became the priority. The war demanded millions of containers, and production had to begin immediately. American manufacturers adapted the design to existing tooling and mass production methods. In the rush, several subtle features were altered or omitted. Welding techniques changed, materials varied, and certain tolerances were loosened to increase output. On paper, the American version looked nearly identical to the German original. By 1942, U.S.-made Jerry cans were rolling off assembly lines by the millions. They improved fuel delivery compared to earlier containers, but frontline troops soon noticed differences. Some leaked. Others dented more easily. The copied design worked, but not as flawlessly as the original. The United States had successfully recognized the value of the Jerry can and acted decisively. When the United States entered World War II, it quickly discovered that its fuel containers were unfit for modern, fast-moving warfare. American forces relied on thin steel cans and large drums that leaked, dented easily, and required tools to open. In training and early deployments, fuel losses were severe. Vehicles often arrived at the front with less gasoline than expected, and refueling under combat conditions was slow and dangerous. The turning point came when Allied forces encountered German fuel cans in North Africa and Europe. British units had already captured and quietly adopted the German design, reporting dramatic reductions in fuel loss. American observers took notice. Field reports sent back to Washington described the Jerry can as superior in nearly every way, stronger, easier to carry, and far more reliable than U.S. equipment. With urgency rising, the U.S. military ordered an immediate evaluation. German cans were shipped back for study, disassembled, and measured in detail. Engineers were instructed to reproduce the design as quickly as possible. Speed, not perfection, became the priority. The war demanded millions of containers, and production had to begin immediately. American manufacturers adapted the design to existing tooling and mass production methods. In the rush, several subtle features were altered or omitted. Welding techniques changed, materials varied, and certain tolerances were loosened to increase output. On paper, the American version looked nearly identical to the German original. By 1942, U.S.-made Jerry cans were rolling off assembly lines by the millions. They improved fuel delivery compared to earlier containers, but frontline troops soon noticed differences. Some leaked. Others dented more easily. The copied design worked, but not as flawlessly as the original. The United States had successfully recognized the value of the Jerry can and acted decisively. On the front lines, small flaws became big problems. Soldiers quickly learned that American-made Jerry cans, though inspired by the German design, often failed under combat conditions. Fuel leaked from weak seams and poorly sealed caps, soaking the ground and wasting precious resources. In North Africa, reports from tank crews described entire gallons lost during transport over rough desert roads, where heat expanded the fuel and vibration rattled the imperfect cans. The consequences went beyond lost fuel. Every spilled drop meant delays in refueling vehicles, slowing the advance of mechanized units. In fast-moving operations, a stalled convoy could be the difference between cutting off an enemy retreat and letting them regroup. Commanders noted that refueling often became a bottleneck, forcing soldiers to spend hours handling cans instead of operating vehicles or engaging the enemy. Soldier diaries and after-action reports reveal frustration and improvised solutions. Crews pried open dented cans, patched leaks with cloth or metal, or even carried extra fuel by hand to compensate for what had spilled en route. These workarounds wasted time, energy, and morale. Men on the front repeatedly noted that while the Jerry can was better than nothing, it did not match the reliability of the German originals they had seen captured. The battlefield lesson was clear: logistics could fail quietly without a shot fired. Even a small design flaw in a fuel container had cascading effects: fuel shortages, stalled units, and exhausted soldiers. In the end, the flawed copy highlighted the value of engineering detail. Victory depended not just on tanks and guns, but on how efficiently the army kept moving.